We're going to put our acid-base knowledge to use in a lab technique called titration, and we use this to find the molarity or the concentration of unknown solutions. So let's begin with how we start our titration. You've already seen a video of how to set that up, and you know you have to use an indicator that changes colors. So this indicator that we use for strong acid, strong base is called phenolphthalein, okay? And here's my pH scale. From 1 through neutral, it is clear. It changes color at 8, and it turns pink, and it stays pink when it becomes basic. So we know our low pH is acidic, and so it's clear under acidic conditions, and it turns pink under basic conditions. At 7, we have a perfectly neutral solution, and that means that my acid equals my base, and this is based on stoichiometry and the coefficients, but to simplify it, it's when I have enough H plus to perfectly react with OH minus, so they're equal, and I make water, and that's why we have a neutral solution. And so at 7, this is called the equivalence point. That's different from when my indicator changes colors. Notice my indicator doesn't change to pink until 8. That's a little past that equivalence point, and so we called the color change the end point. Okay, so let's look at our simple equation here. We have hydrochloric acid is reacting with sodium hydroxide, and when they react perfectly, which happens to be a 1-to-1 ratio, we have a saltwater solution, which is neutral. We have NaCl and H2O. So in my beaker here, I have hydrochloric acid. And if I don't add it perfectly, so here I have 2 HCl's, and let's just say I only put in 1 NaOH, okay? Now, I want you to think about this hydroxide is like a Pac-Man. So I'm going to scoot this over, and here's my 1 hydroxide, and it gobbles this up, and it comes out of solution, and it makes water. Okay, I only put in 1 though, so I still have some H plus in solution, which makes this acidic. My solution's still clear. Let's add another one. So now I've added 2. I'm going to put in this OH. It's going to gobble up this H plus. It's going to come out of solution and make another water. So now these are gone and these are gone, and it did put in 2 Na pluses, right? Because it's NaOH. So when my OH ate this up, my solution's now neutral. I put in enough base to react with those H pluses to turn it into water and make this neutral solution. So over time, or over amount of NaOH, we can make what's called a titration curve. Okay, so this is my titration curve. And what you see here is, just like in my beaker, I started with an acidic solution, so I start at a pH of about 1. So I have H pluses in solution here, okay, because it's acidic. And then right about the time that my OHs are going to equal my H plus, so right when I get about neutral, it jumps up in pH really, really fast. And you can see that my equivalence point and my neutralization point almost take the exact amount of NaOH, which is why that we can use this indicator to change pink at 8. So remember, once my H equals my OH, we have our equivalence point, okay? When it turns pink at 8, that's called our end point. And now, here's my equivalence point. So basically, I just have water in here, right? Everything, all my H pluses got gobbled up by the OHs, and we made a bunch of water. Once I pass my equivalence point, I don't have any more H pluses to react. So when I pass that, what do I have in solution? I have some extra OH minuses, which is why we're now up in this basic range. So what you really need to know for your titration curves is here I start with a pH of 1, which means I start at an acidic solution, and I end around, for this guy, I end around 12. It's usually around 13 or 14. And the difference between the equivalence point is the end point is the equivalence point is where my moles of H plus equals my moles of OH based on stoichiometry. And when I change color, that's called the end point. Okay? So I want to show you what this looks like in my solution. I'm gonna come down, let's see. Okay, so basically here I have my acid solution. I have my indicator in there, and I'm gonna put in a little bit of base. And when I do, that spot right away won't react. And so it should turn pink in just where this is, and then over time it will react. So right now I'm going to put in my NaOH down here, so I won't be neutral yet, but you'll be able to see. Okay, there you can see that very faint pink color. It's pretty hard to see, and if I swirl it, it goes pink and then it goes clear again. That's because my OH was reacting with my H plus. It got gobbled up, but there's still some H plus left. So I'm going to put in some more NaOH. I'm going to pass the neutralization point where it's equal, and I'm going to go to the point where I have too many OHs in solution, which means it's going to turn pink and it's going to stay pink. So I went way past that neutralization point. I have too many OHs in solution. I can put in H pluses and react it back and make it clear again, okay? So now I'm back down at this end and I'm acidic. So this is based on stoichiometry because we have to use these coefficients. If I had CaOH2, I'd need 2 acids for every 1 base. And you will see that in your problems. And we have moles equals moles, and we use this in solution. So to simplify the stoichiometry, we are going to use our moles equals moles, which in solution would be molarity times volume of my acid has to equal molarity times volume of my base. Now, we also have to divide it by our coefficients. So I'm going to call that a big A for the coefficient of the acid and a big B for the coefficient of the base. And here it is a 1-to-1 ratio, which is why we need to start our problems with a balanced equation. So you're going to use this formula, and we are going to equivalence point. This formula can only be used for neutralization problems. If I've gone past or I haven't gone far enough, we will have a limiting reactant problem, and that will be our lesson for tomorrow. So here's an example problem from your workbook. You have a separate worksheet. I'm just using the workbook as my examples. And I'm going to do number 2 because it has different stoichiometry. So the first thing you have to do is you have to write a balanced equation. They gave us our acid and our base. It's a double replacement reaction. So let's put this in brackets so I know my H is now going to dance with my OH. That makes water. And my Na is going to dance with my SO4, so that makes sodium sulfate. How do I get those subscripts? Na is a +1, SO2 is a -2, crisscross applesauce. You get that? And then you have to balance. And now I don't have a 1-to-1 stoichiometry, which is why I wanted to use this. So our formula, if we're going to neutralization, remember we can only use this formula for neutralizing something, is molarity of acid times volume of acid equals molarity of base times my volume of base, and then we have to divide it by the coefficient of my acid and the coefficient of my base. So our problem says how many milliliters, so we're finding out how much of the volume of the sulfuric acid solution does it take to completely neutralize 38 milliliters of 0.75 molar NaOH? So let's plug this in. I have 0.092 molar acid, and I'm looking for my volume of my acid divided by the coefficient of the acid, which is 1, equals, where are we? We have 0.75 molar of NaOH, which is my base, times 38 milliliters of my base, divided by that coefficient for my base, which is 2. And remember, if this is in milliliters, we are going to be solving for milliliters, okay? And that's what they asked for. So you need to rearrange to solve for my volume of my acid. So I'm going to divide both sides by 0.092 to get that alone. So all said and done, you're going to get 154 point blah, 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 blah milliliters. That's 150 milliliters with sig figs because we have only 2 sig figs in 2 of our givens, okay? Actually, 3 of our givens.